In this session, we talk about the solution to question 16, part B of 2020 HSC extension 2. Let in be integral from 0 to pi on 2 of sine to the power of 2n plus 1 of 2 theta d theta, where n can take values from 0 to 1 onwards. And part I proved that in is equal to 2n over 2n plus 1 in minus 1. So for this type of questions, we use integration by parts. So the first step is to write sine 2n plus 1 as sine 2 theta times sine 2 theta to the power of 2n. So when you add the powers back, you end up with the initial statement. So all I've done, I split this into 2n plus 1 into 1 and 2n. Now, as I said, we use integration by parts. Let sine 2 theta be dv and sine 2n of 2 theta be u. And according to integration by parts, we have integral of u dv is equal to uv minus integral of v du. Now dv is sine 2 theta. To go to v, we need to integrate that. So v is integral of this, which will give us minus cos 2 theta over 2. And then going back to our statement for integration by parts, we have integral of u dv is equal to uv. Now my v is that, minus cos theta 2 theta on 2 times by u, which is this, sine to the power of 2n of 2 theta, then minus integral of v du. So minus, and v is minus cos 2 theta on 2 times by du. And if it is my u, then my du is 2n times sine to the power of 2n minus 1 of 2 theta times by 2 cos 2 theta times d theta. And we put the limits because the limits are from 0 to pi on 2. And then here what we've done, this 2 and this 2 cancels out, and 2n can go out, and we get cos 2 theta times cos 2 theta becomes cos squared of 2 theta, and then sine to the power of 2n minus 1 2 theta d theta. This value is going to be 0. And the reason for that is when you sub in pi on 2 for 2 theta, pi on 2 for theta, 2 theta becomes pi, and sine pi is 0. And no matter what this is, going to be 0. And when you sub in 0 also for theta, then sine 0 will be 0 again. You end up with 0 minus 0. So the whole thing becomes 0. Then this becomes only equal to that part. Now, what we can do here, we can write cos squared to the power of 2 theta as 1 minus sine squared of 2 theta. I've done that and then I expanded. So I replace this with 1 minus sine squared of 2 theta. And if you do that and expand it, you end up with sine to the power of 2n minus 1 2 theta minus sine to the power of 2n plus 1 2 theta. All right. Now, this we can 2n minus 1, we can split it into 2 parts, and we can write 2n minus 1 as 2 to the sine to the power of 2n minus 1 plus 1. Minus sine, this stays the way it is. Here, if you look at this closely, this is the original integration we have, where n has been replaced with n minus 1. In other words, this is in minus 1. So then we got 210 here. So this integral becomes 2n, and this integral is in minus 1. Then minus, and this is the original integral which we had. So minus in. Okay, so we started with the original integral, which was in, and we showed that it is equal to this. So if I expand this to n, I get this, and taking in to the other side and factorizing for that will give us in times 1 plus 2n equal to 2n in minus 1. And from here, if you make in the subject, you end up with the answer they have asked us to provide. Okay, that was for part I. For part I deduce that in equal to 2 to the power of 2n times n factorial to the power of 2 times factorial of 2n plus 1. So basically from this, we got to get to this statement. All right, that was what we proved previously. In is equal to 2n plus 1, in minus 1. And we can apply this rule for any value of n. For example, I can replace n with n minus 1 everywhere here. Okay, so that will give me in minus 1 is equal to 2, n replaced with n minus 1, 2 everywhere I'm replacing n with n minus 1, and that becomes in minus 2. What does this tell us is if I write the original statement, in is equal to 2n over 2n plus 1 times, I'm replacing in minus 1 with this. So 2n minus 2, 2n minus 1 times in minus 2. And similarly, in minus 2, if I replace n here with n minus 2, I end up with this. In minus 2 is equal to 2 times n minus 2 over 2 times n minus 2 plus 1 times I3. And if we continue this procedure, at the end we end up with I0 here. And in becomes 2n over 2n plus 1 times 2n minus 2 over 2n minus 1 times 2n minus 4 over 2n minus 2, and etc. until you get to I0. What is I0? I0 is the value of integral, original integral, when we replace n with 0. If you replace n with 0, that becomes just sine 2 theta. And integral of sine 2 theta is minus cos 2 theta over 2. When you replace the value of theta with 0 and pi on 2, you end up with 1. So I0 is equal to 1. Then our In will become that times that times that times by 1. And as you can see, the top value is in each fraction is 1 less than the bottom value. So this will continue until we get to 2/3 times 1. So that becomes our In. And we don't use that for I0 because that will not work for I0. But if you remember from the original value, that was only for n greater than 1. Greater than or equal to. All right, so once you got that, we can actually see what this is going to look like. If you look at this and factorize for 2's in each of them, for example, if I factorize for 2 here, that becomes 2n minus 1. Here, that becomes 2n minus 2, and so on. So basically, I times all the tops, and I put at the top, and I times all the bottoms, and put at the bottom. And I factorize for 2's at the top, except for this, which doesn't have any. So how many 2's are there? You have n number of 2's here, starting from 1 to going to n. So then these 2's will become 2 to the power of n. Then you look at the other values. Apart from 2, you got 1, and all the way n minus 2, n minus 1, and n. So that becomes n factorial. And the denominator, I've just written the denominator the way it is for the time being, so just times everything together. And if you put values for n here, you will end up with 2 times 3 times 4 times 5 times 2n times 2n plus 1. What has happened here? How do I get from this or from this to that? I had 2 to the power of n and n factorial, and I'm timesing the top and the bottom by even numbers. So 2 times 4 times 6 times 2n, up to 2n. And I've done this here because what was happening in the denominator, I had only odd numbers. These are odd numbers. So I need even numbers. And these are the even numbers. And these are the even numbers that we are going to times. 2 times 4 times 6 times 2. And if you times by even numbers, the denominator will change into a factorial, because you've got all the numbers all the way from 2 to 3, 4, and to 2n plus 1. That gives us the factorial of 2n plus 1. And then at the top, we had already 2 to the n times n factorial, and you will get, you had an n factorial here, and if you take, again here, in the even numbers we have, if you take all the 2's out, so how many 2's you're going to have? 2 to the power of, again, n. And these ones that we have 1, 2, 3, all the way to n, will make up your n factorial. So this turns into 2 to the power of n times by m factorial. So as a result, you got m factorial squared, and 2 to the n times by another 2 to the n becomes 2 to the 2. And that is the solution to this part. In the next part, part III, they say if Jn is integral from 0 to 1 of x to the n times 1 minus x to the n dx, prove that Jn is equal to m factorial squared over 2n plus 1 factorial squared. Using the previous integral we had, we are going to have a change of variable and call x as sine to the power of 2 of theta. So in the original, this one that we have, I'm going to replace x with sine squared theta. Let's see how the whole integral will change. Then dx is going to be 2 sine theta cos theta d theta, which becomes sine 2 theta d theta. Then the integral, the original integral Jn will be equal to integral, and my limits will change from 0 to pi on 2, because if x is 0, then theta is 0, and if x is 1, then theta is pi on 2. And the integral will change to 0 to pi on 2 sine squared of theta to the power of n, so in place of x, that's what we have, 1 minus sine squared theta to the power of n, and then in place of dx we have sine 2 theta d theta. Alright, now we replace this with its, using the double angle, we replace this with its value. So sine squared theta is 1 minus cos 2 theta over 2 to the power of n. And that is cos squared theta again, and I'm replacing it with double angle values of that. So it becomes 1 plus cos 2 theta over 2 to the power of n sine 2 theta. Now, we have 2 to the power of n here and 2 to the power of n here. They are constants in the denominator, they can go out. And if you times 1 minus cos 2 theta by 1 plus cos 2 theta, that becomes 1 minus cos squared 2 theta, difference of 2 squares, and then to the power of n sine 2 theta. And here you have 1 over 2 to the power of n times 2 to the power of n becomes 2 to the power of 2n. That is sine squared of 2 theta, and to the power of n becomes sine to the power of 2n of 2 theta times by sine 2 theta, which we have here. Now again, if you add the powers, if you add the power of this and this, you end up with the original equation that we had, original question at the start of this question that we had, part B. And we know the answer to that. We proved the answer to that is 2 to the power of 2n m factorial squared over 2n plus 1 factorial. And we had also 1 over 2 to the power of 2n here. 1 over 2 to the power of 2n here. Now, this 2 to the power of 2n and 2 to the power of 2n cancel out, and we end up with n with factorial of n squared over 2n plus 1 factorial of 2n plus 1. Alright, and at the last part, we have asked to prove that prove that 2 to the power of n times n factorial squared is less than or equal to 2n plus 1 factorial of 2n plus 1. Okay, let's see how we can do that. From part I, we had this. This is the very first thing we proved in part B. We can always say that when you have a sine of an angle, and you take it to a higher power, it becomes less than or equal to what it was, because every time you times sine by itself, it becomes smaller, and the reason for that is sine is between 0 and 1. Every time you times a number by a number between 0 and 1, it becomes less than what it is. So if I take it to the power of k, where k is a whole number, positive whole number, definitely that will be smaller than what it was. Maybe I should write here k equal to 1 to a whole number. Okay, that means if I integrate that, this will be less than if I integrate the same thing with the power of 1. So rather than having 2n plus 1, I just put here 2 theta. So that will give me minus cos 2 theta over 2 from 0 to pi on 2, which if you sub in the values, you end up with 1. So, but this value, we already proved that this integral is equal to 2 to the power of 2n, n factorial over 2n plus 1 factorial. And you can write this as 2 to the power of n, n factorial, all to the power of 2 over 2n plus 1 factorial. And that is, I think, what they asked us to prove. Yeah, 2n n factorial squared is less than. So all we need to do is here just times both sides by 2n plus 1 squared. So you get 2 to the power of n times n factorial to the power of 2. I'm timesing both sides by 2 factorial of 2n plus 1 squared. Yeah, that proves the last part of the question. Thank you very much for your attention.